Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. We've talked a lot about sextants recently, and I thought instead of just talking about the theory, we'd actually go out and do a noon sight. So today I went outside and I did two noon sights. The first was with the Link A12 bubble sextant, and then I used a Davis Mark 25 nautical sextant. Now, solar noon today, September 18th, 2021, was at 13:33 hours Eastern Daylight Time, and that's 17:33 Greenwich Mean Time. And here are the readings that I got. On the bubble sextant, I got 47 degrees 59 minutes, and on the Davis sextant, I got 95 degrees 47 minutes. So let's cue up the music and see how I got these numbers, and then what I'm going to do with them to find my location. And then at the end, we'll have a little contest. Now, a quick word on how these sextant readings were done. This is the A12 sextant. It's designed for use without her horizon in an aircraft. And the way that it works is that it has a chamber right in here that has some xylene in it with a small bubble. And as you look down the eyepiece, you hold it so that the bubble is in the center of the circle of the chamber. Then there is a reflective plate right here of glass. You can see through it, but it'll also reflect the sun. And that reflected sun will bounce up into your eye. And the way that you read the angle is that you put the sun directly in the center of that bubble. Now, this is kind of nice because you take out a couple of the corrections that need to be made. First of all, you do have an index error and you have to account for refraction. But you don't have a semi-diameter and you don't have a dip correction. Now, that's how you do an indirect reading through the eyepiece of this bubble sextant. You can also do a direct reading through the glass, and that's generally used for star readings at night because it'll project an image of that bubble chamber and the bubble on the backside of the glass, much like a reflective gun sight. You just put the star right in the center of the bubble. Another nice thing about the bubble sextant is that you read off the angle directly without any other correction. Now, when you're using the Davis sextant, I did a technique known as an indirect reading with an artificial horizon. So what I did was I put a pan of water on the ground. It's water in a little black dish. I shot my reading directly to the reflected sun in that dish. And as a result, I measure a very large angle that is exactly twice the angle from the horizontal to the altitude of the sun. Now, once again, you do have an index correction that you have to put in. Now, fortunately, my sextant doesn't have one. And you do have to account for refraction. But you don't have to account for dip, nor do you have to account for a semi-diameter. The mechanism is very similar to what we did with the A12, except we read twice the angle that the A12 reads. So we'll go out to my driveway and we'll see me doing the actual readings today at solar noon. Now, prior to filming that, I had gone ahead and gotten the basic angles dialed into the sextants, so I just had some small adjustments to make at solar noon. Now, once we have our readings, we have to go to the Naval Almanac. And here is the Naval Almanac that I'm using for today's readings. On the left side, you'll see a series of numbers. These are dates. For example, that is January 24th. Now, today is September 18th, so we're going to come down to September 18th. And here we are, September 18th, 2021. And we're going to go over to the sun column. Now, my time was between 1700 and 1800 Greenwich Mean Time. The declination of the sun at that time was between 1 degree 35 and a half minutes north and 1 degree 34 and a half minutes north. Now, as our time was approximately halfway between this, I'm going to read this as 1 degree 35 minutes even. And as you see, I've recorded the declination here. That's 1 degree 35.0 minutes north latitude. Next, we have to go ahead and find out what kind of refraction we're dealing with a reading of about 47 degrees above the horizon. Okay, now to find our corrections, now that we have our declination, now we need to find our corrections. Now, as you recall, we were about 47 degrees altitude to the sun. So we're going to go down here to the sun page. Here is where the dip correction would be found. So if you're 10.71 meters, you have to subtract 5.8 minutes from your reading. Now, we don't need to put in a dip correction for either of our readings because we weren't reading from an elevation against the horizon. This is the correction where you have to look down to the horizon from the deck of a ship, and you need to correct for that to get back to your horizontal. We also don't need to correct for our semi-diameter because we're measuring to the center of the sun rather than the lower or the upper limb of the sun. Now, had we been measuring to the lower limb of the sun today, we would have had to add 15.9 minutes to our reading. So, if we were reading to the lower limb of the sun, that semi-diameter correction would have raised us to the center of the sun, which is where we want our reading. What we do need to do, however, is correct for refraction. And the refraction correction is here. Our apparent altitude of the sun was 47 degrees, so we're going to have to subtract 0.8 minutes from our reading. Now let's go ahead and see what we have. Let's start off with the easy one. We'll start with the indirect reading from the A12 bubble sextant. This is our raw reading. This is HS, 47 degrees, 59 minutes. From that, we have to subtract our index error of 5 minutes. That brings us down to 47 degrees, 54 minutes. Then we need to subtract our refraction, and that brings us to 47 degrees, 53.2 minutes. And that is our final corrected reading. Now with the Davis sextant, it's a little bit more difficult because we're reading twice the angle due to the fact that we used an artificial horizon. So the first thing that we're going to need to do is cut this angle in half. Now, half of 95 degrees would be 47 degrees, 30 minutes. Multiply that by 2, you get 95 degrees. To that, we had half of 47 minutes, which is 23.5 minutes. Now, this gives us a total of 47 degrees, 53.5 minutes. To that, we have to subtract our refraction, which is 0.8 minutes. So this 53.3 is going to be 52.7, and we've got that recorded right here. Now let's remind ourselves of how the sextant actually works. All celestial objects will have what's called a geographic position. The spot on the Earth where the object is at your zenith, 90 degrees above your head. Now, at our position, we have a zenith as well, and that's 90 degrees above our heads. Now, we form a local horizontal line perpendicular to that vertical. And I'm also drawing it here to make it a little easier to see because eventually we're going to correct this to the center of the Earth. Now, we're going to measure this angle right here, and that's our altitude of the object. And these are the altitudes that I read. Well, what is that angle? That angle is actually that angle right there. The angle that we want to find is this one, because that will give us our latitude, and that's this angle right here. So that angle equals 90 minus our sextant reading right here. So our next job over here is to find what we call our zenith angle. So let's go ahead and do that. Wait a second. Just before I do that, I want to add one more note, and that's this declination. The declination is the distance to the celestial object, this angle right here, above or below the equator. So in our case, the sun is 1 degree 35 minutes above the equator. So we're going to have to add 1 degree 35 minutes to our final reading to get our true latitude. I'll talk about that again in a minute, but let's go ahead and figure out that zenith angle. Now let me show you a little trick to make your life as a navigator a little easier. We're used to dealing with decimal systems. Here in the United States, our money is in a decimal system. We're used to just dealing with that. So if we want to subtract our measured angle from 90 degrees, it's kind of difficult to do that from 90 degrees. It's a little easier if we convert it to 89 degrees and 60 minutes. And there's our answer. So we got 42 degrees, 6.5 minutes. So we'll write that over here. Let's do the same thing for our reading from the Davis. Okay, and we do that, we get 42 degrees, 7.3 minutes. And I noticed too, we're going to write that over, and I notice I made a slight error over here. Hang on. There we go, got that fixed. That was 42 degrees, 6.8 minutes, not 6.5 minutes. Sorry about that. And the other one that I got was 42 degrees, 7.3 minutes. Well, folks, now for the moment of truth. Even though that was an extraordinarily fast reading and I didn't do all of the corrections that I could have done, I got my location within 7.2 nautical miles from my driveway. Now, the accuracy of a sextant should get you within 15 nautical miles of your position. I beat that by over half. The bottom line is that if I was in an aircraft or on the deck of a ship right now, I could see the airport or the entrance to the port based on that location. I'm close enough to be able to see where I'm going. And that's the goal of the sextant. Now, by the way, just as a little added value to this video, I did a second observation while I was out there. You notice that in the first video, I had a fishing pole tip stuck in the ground, and I had the tip of the shadow marked with some coins. Now, after the video was done, I went back and marked the final position. You'll see that the pennies form a straight line and a dime marks the position of solar noon. That is a geographic east-west line. The fact that that is a straight line confirms that the Earth is a spherical rotating planet. Unless, of course, you can tell me how you're going to get a straight line with a sun moving over a flat Earth. You have enough information to give me the last 2 numbers of the zip code of my town. Go right ahead and put that in the chat. Please don't mention my actual town, but just put in the last 2 numbers of the zip code. Now, for those of you that are particularly ambitious, if you're the first one to put in my 3-digit house number, I'll send you one of my triple water levels. Well, first of all, you do have enough information to do all of that. Second, I hope you'll treat that information with the respect that it deserves. And third, don't fret about any flat earthers finding out where I live. This is so far above them that I'm not worried at all. So, until next time, this is Bob the Science Guy signing out from Northern Michigan. Thank you very much for your support of this channel and helping me indulge my hobby of science. See you soon.